Okay, so thank you so much for your kind presentation, and thank you all for your patience actually, because I'm the last speaker of the day, so I hope you will survive. Yes, I'm Cristina De Nardi from Cardiff University. As you said, I'm a member of the group RM4L. RM4L is an acronym for Resilient Materials for Life, which is an EPSRC funded program grant. And here I present in a part of my research with regards to the use of advanced 3D printed mini-vascular networks for self-healing concrete. Those are the points that I'm going to discuss with you during this session time. I will give you a short presentation, introduction on the biomimicry, and I will give you the idea inspiring the mini-vascular networks. Then I will present the concept of mini-vascular networks. I will describe the healing agents, the mixed components of the concrete, as well as the methodology that we have used. I will present some results with regards to the healing efficacy in terms of flexural strength and stiffness. And then I will close this first part about this special kind of mini-vascular network, so-called TETs, just to open to my current studies, which are on the use of advanced 3D printed mini-vascular networks. I will present you my alternative approach about the healing agents, and I'd like to discuss with you my first results, and I will present my ongoing work. Then, in a non-orthodox way, I'd like to close with the challenges of the research, just because I'm really happy to have your suggestion or contribution. So, the inspiration for the development of vascular networks for self-healing concrete is drawn from the arterial system of the human body, and an ideal vascular system gives good advantages, such as the possibility to supply different healing agents at different time, and to continually supply the healing agents to the damaged patient. However, in the last decades, several researches have been focused on the use of vascular network. However, the advent of a full-scale and constructible vascular network is not yet realized. So we are proposing an alternative approach, which is the use of mini-vascular networks. Basically, mini-vascular network is a 3D printed hollow unit where the healing agent may be stored inside. So basically, the healing agent or the glue can be stored inside the vascular network. It remains dormant until a crack crosses one or more ligaments, breaks, and then releases the healing, agents, and thereby healing the crack. So it is a practical and convenient method to supply the healing agents to a significantly sized crack in a range of 0.1, 0.4 millimeters. Well, the mini-vascular network is a flexible self-healing system, and it's flexible because the wall behavior is strongly dependent on the matrix properties, on the damage, on the level of the damage and the time of the damage, on the healing agent properties, on the design of the mini-vascular networks, and on the 3D printed variables. So at the moment, we have studied two different systems for concrete and for lime-based mortars. So when basically the metric is made of concrete, we have studied medium long-term damage sequences, and we used the sodium silicate as healing agents. You can find some details here already published. And interestingly, when the metric is made of lime-based mortar, we have studied a severe level of damage, and here the healing agent is a solution of Sporosalcina bacteria, Pasteria bacteria, dispersed in the matrix, while the nutrient solution was stored inside the mini-vascular networks. And here you can find very first results in the 5th Historic Mortar Conference proceedings. So when, as I said, the metric is made of concrete, the mini-vascular network has this particular shape, which is a regular tetrahedral unit, and it gives good properties in terms of positive capillary force enough to allow the coming out of the glue, and at the same time the interconnected channels prevent the suction of the liquid hosted inside as well. So at the initial stages of this study involved 3 variants. At the beginning, all of them were printed flat, but then we decide to change the orientation of the printing in order to avoid to have anisotropies along the ligaments, such as delamination or differences in strength. So basically, we were looking for something which is brittle, but strong enough to survive at the mixing phase, to be completely impermeable, and able to have a very good bond properties with the concrete. And we reached the point with the third variant of the TETs. Here are the drawings of the TETs. It is basically size twice of an aggregate particles. On the right, you can see the TETs are really filled with sodium silicate and ready for the cast. They are made of PLA, and PLA is the polylactic acid. It's very common for the 3D printed. It's basically thermoplastic polyester derived from renewable sources. It's biodegradable and technically carbon neutral. But the most important thing is that it doesn't emit toxic fumes when it's incinerated. So it's very useful to prototype or just to prove the concept. Well, as the healing agents, we at the beginning start to use the super glue. So we test a lot of types of cyanoacrylates, but unfortunately, preliminary tests highlighted the tendency to cure after 24 hours. So we move on the use of sodium silicate, which is really widely studied in self-healing concrete, because it has a medium-low viscosity. It reacts easily with the calcium hydroxide present in Portland, just in present with water to form the calcium silicate hydrate gel, which is the main product of the cement hydration. So at the beginning, just to prove the concept, we used a rapid hardening cement in a ratio 1:1 to 2 to 0.45. We cast prismatic samples. We demolded after 6 hours, and then we placed all the sample in the tank. We tested the day after in flexor until the failure or until the crack opening is equal to 0.2 millimeters. We wait 2 weeks for the healing process, and then we retest until failure all the samples. As you can see here on the right, we placed in the third center of the prisms 3 TETs or 2 TETs, and the samples were placed via 10 millimeters concrete spacer. Then we evaluate the healing efficacy by means of the 3-point bend test. So basically, we compare the flexural strength after the healing with the flexural strength in undamaged condition in relation to the level of the damage. And we did the same for the flexural stiffness. Here you can see the samples under the 3-point bend test, which is a classical way to test the concrete. Some breakage evidence when the TETs are filled with water and just some drops of ink. On the right, you can see the samples already tested, and the discoloration of the concrete is a clear evidence of the breakage of the TETs. So here are some results. The presence of TETs marginally reduces the flexural strength of samples tested after 1 day. But on the contrary, on samples cured until 28 days, the flexural strength is almost similar. It's even a little bit more. And moreover, if you have a look at the load CMOD graph here, the presence of TETs seems to bridge the cracks when the majority of the concrete ligaments are already lost, and it acts as a kind of reinforcement. Then we did 3 damage healing cycles. Here you can see just 2 because we didn't have any healing after the second one. So for control samples, after the first damage healing cycles and the second healing cycles, well, the healing efficacy is almost negligible, and it is almost worse when the samples contained 2 empty TETs. Here you can see samples containing 2 TETs and 3 TETs, respectively on the left and on the right. after the first damage and healing cycles, in samples containing 2 tests, we can see a healing recovery in terms of strength around 19% and then 20% in samples containing 3 tests. And for what concerns the stiffness, we have a healing around 75% and 79%. After the second healing, the second damage healing cycles, the trend is still positive. And in terms of strength, the recovery is around 11% in both cases. And considering just the stiffness, we are around 40% and 33%. Well, when we damage and heal again, so after the third damage healing cycles, it appears that the concrete test system have consumed all the healing agents stored inside the tests. So the recovery is almost negligible. However, we can see a positive trend in terms of stiffness. Well, then we move on a kind of sensitivity studies of the variable that might affect the healing behavior. So we studied the level of the damage, increasing the CMOD until 0.4, so it is the double that the previous one. And as you can see from here, even when after the pre-damage phase, the residual flexural strength is close to 100 Newton, still we have a positive trend in terms of recovery of strength and stiffness. And this value is almost similar to the previous case. And we also have a positive trend after the second healing cycles. However, when we just add an extra amount of water to the reaction between the sodium silicate and the calcium dioxide present in the matrix, it seems to slightly affect the healing efficacy in terms even for the strength and for the stiffness. And when we prolong the time of the healing, is of limited benefit actually. So if we have to just try to remark something, well, actually this shape have responded effectively to the damage. We have a good bond between the tests and the concrete. It appears to have a kind of ceiling value in terms of strength and stiffness. So we reached 20% in terms of strength and 75–80% in terms of stiffness. And the number of tests seems not to really affect the healing behavior. So that as a shape is a good system for perfusible healing behavior and is available for multiple events if we give the appropriate selection of the healing agents. So now the idea is how we can improve the tests in order to accommodate a wider range of healing agents. Well, this is just one answer, and the answer is if we host a bicomponent healing agents, we should try to use a dual channel test. Again, we studied 3 variants of the same shape. And basically, we focus on the outer wall print speed and the external and the inner wall thickness in order to make both the channel completely impermeable, one each other. And then we add some punctual supports to the inner channel at the corner in order to give more stability to the printing space. Well, the third variant gives the best performance. It provides a very good balance between the strength, so we reach the point to break when we want, and to the impermeability. It prevents the premature healing curing, and then we rupture at the appropriate crack opening. Here again, the drawings, the complete drawings of the dual channel tests. On the right, you have 4 steps of the printing. Basically, the proportion between the inner channel volume and the external one is 1 to 30. So we follow 2 strategies for the bicomponent healing agents. The first was just to test something from the market, so something which is commercially available, and we tested an epoxy resin in solution. So basically, both the components have low viscosity, so the injection was really easy. And And even if, let's say, it's light hydrophilic, so the hydrophoby allowed to have a good penetration, it seems that the resins soften the PLA, and just because it triggers an alteration of the PLA, the consequence is an incomplete mixing of the two components, so basically they didn't polymerize very well. And then we moved on a tailored self-healing bicomponent glue, where when we use the pre-polymer, it is a polyurethane pre-polymer and an amine-based hardener. We are working together with Paul Ellison and Willem Evans here at the Cardiff University. First of all, we trialed pre-polymer polyurethane and the hardener in 2 different hollow channels, and they work really very well, achieved over 100% in terms of strength. But when the pre-polymer, so when the polyurethane basically is stored inside the minivascular network, is not stable. So we need to work a little bit on the stability of the pre-polymer. And another idea is to work on the hardener. So we are trying to incorporate into the concrete via pozzolanic reaction the amine functionalized silica nanoparticles, and we are trying to introduce the amine functional group into the cementitious matrix as well. So an alternative approach would be to just use or to add a promoter of healing when the healing agent remains the sodium silicate. We tested different solutions actually. One is a nanosilica dispersion, and it's a colloidal aqueous dispersion, and it's stabilized. The idea is that both components are good, so they are compatible with the matrix and with the sodium silicate. However, it seems that the solvent reacts with the PLA. So again, we have a problem of reactivity of the oxidized group of the PLA with everything basically we put inside. But we still have a positive value when we consider the combination of the nanolime. So we have the sodium silicate, the nanolime, and the nanosilica as well. When we use a nanolime dispersion and the sodium silicate, we have an excellent compatibility. So basically, we are giving to the system more calcium hydroxide to the system, and we are working on the carbonation. Basically, we have a good compatibility, and we have really good effect in terms of healing. So the differences between this second one trial and the first one is around 10%. So I think it will be promising. So for what concerns the futures work, we are now exploring different variables. So we are trying to evaluate different diluent and try to see if we have less reactivity with the PLA. We are trying to promote more nanolime, so basically working on the concentration of the solution, and we ask the collaboration of the University of Florence. And we will try to evaluate if reducted moisture in the environmental condition may really affect the mechanical behavior, so we not have so diluent reaction. So from what concerns the challenges, and I'm asking your help in solving some of them, basically we will work on manufacturing minivascular networks, because now we are printed once at one time, so it's not an industrial way to produce the minivascular networks. We are looking for an inert thermoplastic polymer with low strain, but basically with an inert behavior. And we are looking for different healing agents, monocomponent or bicomponent, with low viscosity, perhaps with expensive curing action, with good encapsulation stability and good mechanical properties. And then I'd like to just thanks the BSRC for supporting my project and all the RM4L group. And I hope to see you in person in our conference we are organizing organizing the conference in Cambridge the next year in September. And thank you for your attention.